Are you one of those people who sat in maths class and wondered, when will this stuff ever be useful? Well, your long wait is finally over. We're at the 17th meeting of the Maths in Industry Study Group right here at the University of Zululand in South Africa to discover how real-world problems are being solved with mathematics.
We've been hearing all about global warming, but today we're going to be having a conversation about a much more local type of warming. This is called urban heat islands. It turns out that the very structures that we've created to keep us comfortable are contributing to increased temperatures within cities. So we've gathered at the University of Zululand with researchers from around the world who are collaborating to try and address some of these complex challenges. I'm here with Gideon Fareo, who's a senior lecturer at Wits University. His specialization is in fluid mechanics and differential equations. And he's also joined by Narini Mualal, a lecturer in mathematics at the Durban University of Technology. What do we mean by the urban heat island? Gideon.
Island is just an urban area that is significantly warmer than the surrounding, areas, surrounding rural, settlements.
Okay, and why do urban areas become hotter than the surrounding areas?
Mainly because of the fact that in urban centers we have, blocks of buildings that are packed together, made of concrete. We've got, improved facilities, tarred roads, colored in black, black tarmacs. These structures also they help to accept heat and store heat. So as a result, during the evenings, when the impact of radiation is gone from the sun, we have these structures that are meant to keep us comfortable, now releasing the heat they've stored during the day. And this process ends up bringing about an heightened temperature compared to the surrounding rural areas, where there are less structures that can absorb this heat.
And why are these elevated temperatures a problem in cities?
We are forced to seek, technologies that can help to keep us cool, like, the fanning system, the refrigerating system, and the likes. I mean, naturally, too much hotness is definitely not good for humans. We want to, exist in a cooler space, in a sense, yeah.
To a certain extent, this must actually be contributing to additional energy consumption if we utilize air conditioners, etc., to cool down cities.
This further heating up ends up, taking so much of our energy in the form of electricity. So we're, spending more money, buying electricity, putting pressure on our power grid nationally and the likes.
And Narini, what can be done? What are some of the ways in which this urban heat island can be addressed?
So, of course, the ideal solution to this would be to not have as many buildings as we do. But we know that the very nature of urbanization is a mushrooming of buildings. It's an ongoing process that we can't do much about. So the next best option would be to then plant more trees, around our buildings to create more shade, thereby, improve the cooling. But then in urban areas, space is often a problem. So this is sometimes not possible as well. What has been established, which is really the subject of our project at the moment, is the installation of a green roof. So what this is the planting of plants on rooftops, not just any type of plants, but probably succulent plants which have the ability to absorb and hold water, retain their moisture. And in doing so, what happens is they absorb energy from the sun in order to photosynthesize. So energy is used up, that heat energy is used up. It's not wasted or doesn't go out into the atmosphere and contribute to the heating process. At the same time, these plants undergo a process known as evapotranspiration. This has a cooling effect. We know that the green roof, it has been established that the green roof is actually a method or a mechanism of insulation for homes, for the insides of homes. Our project is looking into how the green roof can actually contribute to the cooling of the air temperature outside as well.
Okay, fantastic. So I'd like to just understand this this process. You're suggesting that by placing plants on the tops of buildings, by planting up the tops of buildings, you could reduce the extent to which cities heat up during the day and reduce the effect of the heat island. How do we evaluate the extent to which we would need to do such planting in order to get the kind of cooling we're looking for? So how much of a given city would need to be planted in order to get some kind of cooling effect?
That would actually be the end result of the work that we are currently doing. Once a model has been built, and if it is found to work, in other words, to be successful, what would have to happen is a feasibility study would have to be undertaken in order to decide to what extent the green roofs would contribute to a cooler climate. This would also perhaps involve a study of optimization to decide what percentage, for example, of a city would be under green roof at what cost, at the lowest possible cost.
So I'd like to welcome Professor Graham Hocking from Murdoch University in Australia. He is an applied mathematician, and also Herman Mambili Mambundu, who is a lecturer at UKZN and lectures in mathematical biology and fluid mechanics. Welcome, both of you. How do we need mathematicians, and how can mathematicians help us to solve this kind of a problem?
Well, mathematics can be used for nearly anything, really, to come up with models to describe what's going on. And the models are really just a complicated system of bookkeeping where you can take into account all of the factors that influence a certain process. So in this particular problem, you might be looking at how much heat is coming in from the atmosphere, how much heat is being absorbed by the buildings, how much is being reflected back out into the atmosphere, and then you can examine what the effect of the plants might be on that. Of course, this is a very, very complicated problem because once you start to heat buildings, the air starts to move and you get lots of other processes involved. So one of the skills of mathematicians is to decompose the problem into smaller aspects and consider them one by one and then see how they interact together to get a full understanding of what the impact of greening the roofs might be. For example, it might be that locally it gets cooler, but then other heat goes somewhere else, which might have a negative impact. So without having to build an imaginary city and paint some of the roofs green and some other colours and put in concrete and other materials, you can come up with a model that describes all of that very simply, sometimes in a computer simulation. So it's much, much cheaper. You can analyse all the different factors together and then try to come up with sensible solutions. Once you've done that, of course, you need to collect data and check that all of the things you're doing are correct.
Has this approach been used to address this problem elsewhere in the world?
They have been verified to serve as good insulators, for buildings directly below them. Not much study has been done when it comes to ascertaining or verifying the relevance of green roofs when it comes to insulating cities.
And Graham, what mathematical approaches have you been applying to this problem this week?
There are varying levels of mathematics complexity that can be used, but the goal of something like the Maths in Industry study group is often to find the simplest model that encapsulates all of the main features. So you're looking for the variables and parameters and quantities that are the main ones in driving the process. So ideally, you end up with very simple equations for those who know differential equations, but then the level of complexity can go up to very complicated, large numbers of equations altogether. The thing that mathematicians can do usually is resolve which are the really important features in such systems so that we can then pick out, we don't need to worry about those things and we do need to worry about those things. In this particular example, you have equations like the heat equation, which describes the movement of heat in objects. And so that's a good one to look at the heating of the building and what's the effect of the green roof on that. But then you could extend that into much more complicated systems like the equations of fluid dynamics, which are the things that meteorologists use to predict the weather. So they predict how the air will move in response to heating and so on. So there are varying layers of complexity that you can include, ranging from very simple equations up to very, very complicated equations.
Herman, I understand that you've got a little bit of knowledge about a project that's taken place in the city of Johannesburg. Could you tell us a little bit more about that project and how it was, what it aimed to achieve?
The project in the city of Johannesburg was first created to give job opportunities to people living around the city in Hillbrow. So the idea was more about green gardens because people around there could not find spaces to farm on the ground. So they came up with this great idea of farming on top of buildings. This was not related directly to urban heat islands, but as I said now, it can come in to help the city of Johannesburg if we ever found out that green roofs can actually contribute to reducing the heat in the cities.
And I also understand that there's been some research done about the potential for green roofs to reduce water runoff during flooding events.
Yes. It's well known that plants can retain water coming from the rain. So I think 6% of rainwater can be retained by plants, 50 to 60%. And in that sense, they will reduce the amount of water which goes into drainage, and that might cause flooding in the city.
So how do you anticipate that this information coming out of this collaboration could be utilized by people to solve some of these challenges?
First of all, as my colleague was saying, mathematics is a very powerful tool. We can mimic most phenomenon in nature. Actually, every phenomenon in nature can be mimicked by mathematics. And once we understand how it works, then we can find process into which we can use the models to predict what can happen in the future. In terms of green roof, the way I see it, you may just look at reducing the heat around the urban city, but I think it has further implication it's going to have further implication in the future, in the sense that once you have green roof on top of buildings, and you know that our cities are very populated in cars and carbon dioxide emissions. So it's a well-known fact that plants absorb carbon dioxide. So that will also reduce the emission of carbon dioxide around the urban cities.
Absolutely. It looks like there are multiple benefits. In reflecting on this process that you've been through in the last couple of days at the Maths and Industry Study Group, I'd like to get a couple of your thoughts about what the impacts are of bringing together people from different disciplines to try and understand issues.
For me, it's been a very enriching exercise, and I was lucky that I was in the first meeting in Johannesburg. I was still an honor student at the time at Wits University, and when the first meeting happened at Wits, and it opened my eyes about what I can do with mathematics, because I met a lot of experts from different universities. We came up with the knowledge of how to use mathematics to understand nature and model any process around us. So it's been very enriching, and this is my third meeting now, and I always learn each time I come to these meetings because we meet different people from different backgrounds, and mostly when we discuss about problem, we have different view on the problem, and that can actually help you to grow in as a mathematician and a researcher as well.
Mathematics in industry study groups are conducted all over the world, and I've probably attended 30 or 40 now. When I started, I was like Herman. I really didn't know much about how to use mathematics in different problems. We'd done theoretical things, of course, in class, but we'd never really looked at real problems. Bringing together people from all different backgrounds, you very quickly understand how knowledgeable people are about different things, and you take it on and you learn it yourself. And one of the big things that you learn is how to interact with people from industry, and they quite often think the same way as you, but quite often they don't think the same way as you. They're very interested in answers, not necessarily how you get them, but they're also very interested in the thought process that goes behind it, because mathematicians in some ways tend to think a little differently to perhaps engineers the engineer will tend to look at the whole problem and try to come up with a good solution to the whole problem. And mathematicians are trained more to break things down into smaller groups. People from different backgrounds, because of their different training, have a very different approach to problem solving. Bringing them all together gives you so many more options of how to approach problems and how to think about them. And one of the big benefits that I've observed over the years is how students in particular who come along learn and become enthused by doing it and become keen to get out there and help the world by solving real problems and using their skills, and also becoming more diverse themselves and learning more about different areas. So I think mathematics in industry generally is an excellent vehicle for especially students to learn and become better, as Herman was saying, become better mathematicians and better researchers, but also better citizens in terms of making the world a little better if we can.
So I just want to say that contrary to what Graham said, he's had about 30-odd experiences with MISG. For me, it has been my first. Although I've been in education for a long time, this is the first time that I've attended a maths and industry study group workshop. And to be honest, it's not at all what I'd been expecting it to be. What I had envisaged was that, we'd have the real people from industry saying, here's a problem that I have. Can you provide me with the solution? That said, I have to say this has been such an interesting experience. It has been wonderful meeting and networking and collaborating with people from different backgrounds, different areas of mathematics. It's taken me out of my comfort zone in that I came in here, and when I had first spoken to Gideon, I asked him, so what is the urban heat problem? What kind of mathematics does it involve? And he said to me, well, it involves some partial differential equations. And whilst I've worked with partial differential equations within the context of relativity, it was not what I'd been expecting here. So, I do believe that an experience like this is a growing experience for anybody who's willing to learn. Beyond that, I think we formed some associations and relationships that go beyond this workshop. There's collaboration and networking that is useful, and these are the kinds of friendships and associations that last way beyond the MISG industry workshop.
I was going to say that problems are not localized, you see. So from an environmental point of view, technological point of view, is global. So the problem of urban heat island, for example, is not local to our communities alone. It is a problem even in developed countries. What you find out then is that when we have these study group workshops, and we have friends and colleagues from overseas coming in to look at our problems, they then also bring with them these experiences, that they've had, looking at similar problems in the past, because study groups, like my colleague here says, happens in many other countries of the world. I've been to the study group, European study group, when it held in the UK, and these friends and colleagues coming over, what you find out is that they also kind of contribute as well. Okay, we had this problem as well over a couple of years ago, and we did this. This is the kind of model we used. And
Fantastic, and thank you. And bringing the conversation back to the urban heat island and green roofs, it's not a concept I had heard of before. It's not something that I had encountered. So to what extent do you believe in the idea of green roofs? And do you believe that it's something that needs to be promulgated and made more available as a technology?
Of course, something like the green roofs is one potential technology, and we have to be careful not to say that's the only one. The sort of thing we're doing here is testing out how it would work and whether it's feasible. And maybe at another MISG in the future, someone can bring along another technology that might have the same effect, and we can compare the two. The danger when you're working on one particular problem is that you become focused on that as the solution, when of course there are many, many solutions. The point about doing this work is to examine whether it's viable, how useful it is, and of course there are lots of other issues that are associated with this, like the cost and so on, which would need to be considered in the follow-up of what happens in the maths study group. It may not be feasible for other reasons, so even if it's quite a good technology, it may turn out to be very expensive. I suspect it's not. I suspect it's quite cheap. But I think you need to be mindful that we're working on one aspect, and so it can be very useful and it may have lots of other benefits. But then you also need to think about what other possibilities there might be that could do the same thing in different ways. And maybe the end result will be a combination of all of those things. The point about having the mathematical models and the tools to do this without having to build big models, without having to collect masses of data, is that we can do it very cheaply and very efficiently and work out what are the governing factors that really make those decisions.
Absolutely. Any other comments or ideas that people wanted to share?
For me, I come from Gabon, and the very first thing when I get to my home city, the capital Libreville, that I notice is the excessive heat. And most of Libreville is built like in Johannesburg of concrete structures with paved road and so on. So, but actually when I look at all the projects that we're presenting on the first day, and I thought that the Green Roof project will actually, if it works, if it's proven to work, can actually benefit my city. The problem in my city is when the heat rises, we have certain diseases that appear like malaria, because mosquitoes like to breed in very hot temperature. And the second problem, which is runoff of rainwater, it rains a lot in Gabon. It's a rainforest. The mosquito, that secondary water stagnates in many parts of the city, and that gives an opportunity for mosquito to reproduce even more. So I'm hoping that green roofs will actually bring a relief to this kind of problems, because that will reduce the incidence in malaria, because malaria is like number one killer in my country at the moment, and that can help in reducing the incidence in malaria-related death in the country.
Absolutely. Well, it's been a fascinating journey to understand this problem that I wasn't even aware of before, and how you are bringing together minds and approaches to deal with it. And I think it's an exciting story, and we'll look forward to how it develops. I look forward to hearing more from each of you as the program progresses. Thanks very much for participating in this conversation.
Thanks.
Thank you.
Thank you.
The South African Mathematics and Industry Study Group was founded by Professor David Mason in 2004 at Wits University and has created exciting opportunities for collaboration between mathematics researchers and industries facing complex problems. The 2020 event is hosted at the University of Zululand and is supported by the DSI NRF Center of Excellence in Mathematical and Statistical Sciences, the Herman Althover Trust, and the African Institute for Mathematical Sciences. This podcast was sponsored by the Center of Excellence in Mathematical and Statistical Sciences, an initiative of the Department of Science and Innovation and the National Research Foundation.